A language model begins with a narrow learning problem. Given some text, predict what comes next. Everything that later looks like explanation, translation, coding, or conversation is built on repeated next token prediction. To make that concrete, follow one small example through one small model. The sentence is, "The moon rose over the quiet lake." During training, the model does not receive the sentence as a fact to memorize. It receives a sequence in which each position creates a prediction problem. The model will turn text into token identifiers, convert those identifiers into vectors, mix information through transformer layers, and produce a score for every possible next token. A probability distribution will emerge from those scores. The probability assigned to the actual next token will become a loss. Backpropagation will trace that loss through the computation, and an optimizer will make a small change to the model's parameters. One example does almost nothing by itself, but this exact causal chain, repeated over enormous collections of text, is how a language model learns. The sentence contains several training examples at once. After the target is moon. After the moon, the target is rose. After the moon rose, the target is over. The context grows one position at a time, while the desired answer is always the next piece of the original text. Training software represents this efficiently with two aligned rows. The input row contains every token except the final one. The target row contains every token except the first one. The target row is shifted one position to the left relative to the input. This arrangement allows the model to make many next token predictions in parallel. It must not use information from future positions, so attention is masked. The representation at moon may use the and moon, but not rose or anything after it. The same model parameters are applied at every position. A short sequence therefore supplies several related learning signals, and a batch of sequences supplies thousands. The training objective remains simple even when the amount of parallel work becomes large.
Before the model can process the sentence, a tokenizer divides it into discrete units. A token may be a word, part of a word, punctuation, white space, or a byte-level fragment. For this example, imagine that the tokenizer produces 7 pieces: the, moon, rose, over, the, quiet, and lake. The leading spaces are part of several pieces. That detail matters because tokenizers preserve enough information to reconstruct the original text exactly. The vocabulary is a fixed list of allowed pieces. Each piece has an integer identifier. Common fragments often receive compact single tokens, while unusual names or unfamiliar strings may become several tokens. Tokenization therefore affects both meaning and cost. A sentence represented by 7 tokens requires 7 positions of transformer work. The same visible sentence under another vocabulary might require 10 or 12. The model never manipulates the printed words directly. From this point onward, the tokens are the units whose identities, positions, and relationships will be represented numerically. Suppose the 7 token identifiers are 314, 8821, 5410, 927, 279, 6437, and 9102. These numbers are addresses, not measurements. Token 9102 is not larger or more important than token 279. The identifiers simply select rows from learned tables. Treating them as ordinary numbers would invent relationships that the vocabulary never intended. The most important table is the embedding matrix. It has one row for every token in the vocabulary and one column for every feature in the model's hidden width. If the vocabulary contains 10,000 tokens and the hidden width is 8, the embedding matrix has shape 10,000 by 8. Identifier 314 selects row 314. Identifier 8821 selects row 8821. A fast indexed lookup retrieves all 7 rows. The result is no longer a sequence of integers. It is a sequence of learned vectors, one vector for each token position. That change moves the data from symbolic addresses into the continuous space where neural network computation can begin.
An embedding vector is a bundle of learned coordinates. In the tiny model, every token becomes 8 numbers. At initialization, those numbers are small and mostly random. Training gradually organizes them so that useful distinctions can be expressed by later layers. No single coordinate has to mean noun, moon, or night. Meaning is distributed across dimensions and across the transformations that follow. With one sentence in the batch, 7 token positions, and 8 hidden features, the embedding tensor has shape 1 by 7 by 8. These axes have different roles.
The batch axis separates independent examples. The sequence axis preserves token order. The hidden axis carries features. Naming the axes prevents many mistakes because the same total number of values can represent very different structures. The tensor now holds 56 floating point values. Those values are the model's initial internal state for this example. They will travel through the transformer while their shape remains mostly stable. Embedding lookup identifies which token occupies each slot, but it does not by itself describe the slot's position. A transformer applies similar operations across the sequence, so the model needs an explicit way to distinguish the first token from the fifth. Positional information supplies that distinction. Different architectures add learned position vectors, rotate features according to position, or use related mechanisms inside attention. For the mental model, imagine that each token vector receives a position-dependent adjustment. The vector for the is marked as position 0. Moon is position 1. Rose is position 2, and so on. The shape remains 1 by 7 by 8, but the values now encode both identity and order. This allows attention to learn directional patterns, such as looking backward to a subject, preferring nearby punctuation, or relating an adjective to the noun that follows. Position is not a decorative label. It changes the numerical state that the model will use to decide which earlier information matters at each prediction point.
The token and position information now enters the residual stream. Think of this stream as a shared workspace that runs through every transformer layer. Each submodule reads the current state, computes an update, and adds that update back to the stream. The original state is therefore not replaced all at once. It remains available while attention and the feed-forward network contribute refinements. Residual addition makes deep models easier to train because information and gradients have direct paths across many layers. If a submodule initially produces a weak update, the surrounding representation can still pass through. Over time, different layers learn to write different kinds of information into the same hidden space. The shape remains 1 by 7 by 8 in the tiny model, but the interpretation of those values becomes richer. At the entrance, they mostly reflect token identity and position. After several layers, they can represent context-dependent properties, relationships, and evidence useful for predicting what follows. Before a major transformation, the model often normalizes the hidden state. Values can grow or shrink unevenly as they pass through many additions. If scale drifts too far, optimization becomes unstable, and one set of features can dominate simply because its numbers are large. Normalization measures the feature values at a position and rescales them into a controlled range. Learned gain parameters then allow the model to restore useful differences. Normalization does not erase the token's information. It changes the numerical coordinate system in which the next operation works. In a pre-normalized transformer, attention and the feed-forward network each receive a normalized view, while their outputs are added to the unnormalized residual stream. This separation gives the submodules predictable inputs and preserves the accumulating workspace. The distinction matters during backpropagation because gradients pass through both the transformation path and the direct residual path. Stability is not produced by one trick. It comes from the interaction of normalization, residual connections, initialization, learning rate, and precision.
Self-attention begins by projecting the normalized state into 3 related views: queries, keys, and values. Each projection is a matrix multiplication with learned weights. A query represents what the current position is looking for. A key represents how an earlier position can be matched. A value represents the information that can be carried forward if that position receives attention. For 7 positions, the model produces 7 queries, 7 keys, and 7 values. Multiple attention heads can perform this process in smaller feature spaces, allowing different relationship patterns to coexist. One head might become useful for nearby syntax, another for matching repeated names, and another for broader topic signals. These roles are not assigned by a programmer. They emerge when the learned projections help reduce prediction loss. Queries, keys, and values are simply linear transformations at first. Their functional interpretation comes from how they participate in scoring, mixing, and the downstream objective. Each query is compared with the keys at positions it is allowed to see. The comparison is a dot product. Large positive alignment produces a high score. Weak or opposing alignment produces a lower score. Across 7 positions, the scores form a 7 by 7 table. The causal mask blocks entries that point into the future. At the position after quiet, the model may use the moon rose over the quiet, but it may not inspect lake because lake is the target it is supposed to predict. The allowed scores are scaled and passed through softmax, so that each row becomes a set of non-negative weights summing to 1. These weights mix the value vectors. A position can gather a little information from several earlier tokens or concentrate on one strong source. The output has the same sequence length and returns to the model width after the attention heads are combined. Attention therefore converts pairwise relationships into a context-sensitive update for every position. The weighted value mixtures from all heads are concatenated and projected back into the model's hidden width. This projection lets the model combine specialized head outputs into one update. The update is then added to the residual stream. The vector at each token position now reflects not only that token and its location, but also selected evidence from the earlier context. At the prediction position following quiet, the state may carry evidence that the sequence describes a scene, that quiet behaves like an adjective, and that a noun is likely to follow. Those descriptions are human interpretations of a distributed numerical process, not named fields stored in the vector. The useful test is operational. Does the updated representation make the correct next token more probable? If so, gradients will tend to reinforce the projections and attention patterns that contributed. If not, the loss will push them in another direction. Attention is valuable because it creates a content-dependent route through the sequence, rather than applying the same fixed mixture everywhere. After attention updates the relationships among positions, a feed-forward network, often called the MLP, transforms each position independently. The same MLP weights are reused at every sequence position. Its first projection expands the hidden width into a larger intermediate space. A nonlinear activation controls which combinations become strong. A second projection contracts the result back to the residual width. Attention decides where information can come from. The MLP decides how the information already present at a position should be transformed. In a larger model, the intermediate width may be several times the residual width, so these projections account for a substantial fraction of the parameters and compute. The MLP output is added back to the residual stream, preserving the same 1 by 7 by 8 shape in the tiny example. Attention and MLP together form one transformer block. Repeating blocks lets later layers operate on representations that earlier layers have already contextualized and transformed.
A transformer stacks many blocks. The residual stream crosses each one, while attention and MLP updates accumulate. The outer shape can remain unchanged from the first embedding to the final hidden state, even though the computation inside each layer uses several temporary shapes. This stable interface is one reason transformer components can be repeated cleanly. Early layers may develop local features, middle layers may combine broader relationships, and later layers may assemble evidence directly useful for the output distribution. These are tendencies rather than rigid assignments. What matters for the next token objective is the hidden vector at each prediction position. For the target lake, the relevant vector is the state after processing the context through quiet. That 8-number vector is the compressed result of token identity, order, attention to earlier positions, nonlinear transformations, and residual accumulation. It still is not a probability distribution. One more learned projection must translate hidden features into scores over the vocabulary. The output projection maps the final hidden vector into one score for every vocabulary token. With a 10,000 token vocabulary, 8 hidden features become 10,000 numbers. These raw scores are called logits. A logit is not a probability. It can be positive or negative, and the logits do not have to sum to anything. Their relative differences determine the distribution that follows. Imagine that the model assigns the candidate lake a logit of 1.2, night a logit of 1.0, room a logit of 0.3, and thousands of other tokens lower scores. The correct token is near the top, but not decisively favored. A model at random initialization would produce largely arbitrary rankings. A trained model produces structured rankings because the output weights and hidden state have been shaped by many previous errors. Weight tying may reuse the embedding matrix for this output projection, but the causal role remains the same. translate the contextual representation into vocabulary-level evidence.
Softmax converts logits into probabilities. It exponentiates each score and divides by the sum across the vocabulary. The result is non-negative and sums to 1. Adding the same constant to every logit does not change the probabilities, so only relative gaps matter. For numerical stability, implementations subtract the largest logit before exponentiating. Suppose the correct token lake receives probability 0.18. That means the model assigns 18% of its probability mass to the correct continuation and distributes the remaining 82% among alternatives. It may still predict lake if that is the largest individual probability, but training asks for more than winning the ranking. It rewards the model for concentrating probability on what actually occurred. Temperature can later reshape a distribution during generation, but training normally evaluates the model's direct distribution. The target probability now provides the quantity needed to calculate a scalar error. For one target, cross-entropy loss is the negative logarithm of the probability assigned to the correct token. With target probability 0.18, the loss is about 1.715 in natural log units. If the model assigned probability 1/2, the loss would be about 0.693. If it assigned only 1%, the loss would rise to about 4.6. The logarithm makes confident mistakes especially expensive. Training computes this loss at every valid target position and averages or sums the values according to the chosen reduction. Padding positions can be masked so they contribute nothing. The result for a batch is a single scalar objective, but that scalar condenses thousands of vocabulary distributions. Lower average cross-entropy means the model places more probability on the observed text. Perplexity is the exponential of the average loss and can be interpreted loosely as an effective number of plausible choices, provided the tokenization and evaluation setup are held constant.
The path from token identifiers to loss forms a computation graph. Nodes represent intermediate tensors. Edges represent operations, such as lookup, addition, normalization, matrix multiplication, softmax, and logarithm. The graph also contains every parameter that influenced the result: embedding rows, attention projections, MLP weights, normalization gains, and output weights. During training, the system retains enough intermediate information to differentiate the loss with respect to those parameters. This is why training consumes more memory than a simple forward pass. Activations such as normalized states, attention probabilities, and MLP intermediates may be needed later during backpropagation. Automatic differentiation records the operation structure, while optimized kernels carry out the numerical work. The model has now produced an answer and a score for that answer. Learning begins only when the scalar loss is traced backward through this graph to determine how each participating parameter affected the error. Backpropagation starts at the loss and walks through the graph in reverse. At each operation, a local derivative describes how a small change in its input would change its output. The chain rule combines that local sensitivity with the gradient arriving from later operations. The result is a gradient for each input, which continues backward. The gradient is not a correction value or a replacement weight. It is a local slope. Near the current parameter setting, it estimates how the loss would change if that parameter moved slightly. Parameters reused across positions receive contributions from every place they participated. Those contributions accumulate because the shared weight affected many predictions. The output projection receives a direct signal from the difference between predicted probabilities and the target. Earlier layers receive transform signals that pass through matrix multiplications, residual additions, nonlinearities, normalization, and attention. Residual paths help gradients reach earlier layers without depending entirely on a long chain of transformations.
Every parameter gradient has the same shape as the parameter it will update. If a projection weight has shape 8 by 8, its gradient is 8 by 8. If an embedding table has 10,000 rows and 8 columns, its gradient has that logical shape, although only the rows selected by the batch may receive direct lookup contributions. Shape is a powerful correctness check because it reveals which dimensions must survive and which must be reduced. For a matrix multiplication, backward computation uses transposed matrices to align the shared dimensions. If an input matrix times a weight matrix produces an output, one backward path combines the output gradient with the transposed weight to recover the input gradient. Another combines the transposed input with the output gradient to recover the weight gradient. Across a batch and sequence, repeated evidence is summed into shared parameter gradients. The backward path therefore performs substantial matrix multiplication of its own. It is not bookkeeping around the forward computation, it is another major computational phase. Once gradients have been computed, an optimizer turns them into parameter updates. The simplest rule, stochastic gradient descent, subtracts the learning rate times the gradient. Atom keeps moving averages of recent gradients and squared gradients, using them to scale the step for each parameter. This adds optimizer state in memory, but it often makes training large networks more manageable. The learning rate determines how far the model moves. A step that is too small wastes computation and learns slowly. A step that is too large can overshoot useful regions or destabilize the entire run. Schedules often begin with a warm-up, reach a peak, and then decay. Gradient clipping can limit the effect of unusually large updates. Weight decay can gently discourage some parameter growth. None of these controls changes the central objective. They govern how the model follows the information contained in gradients. For this example, the optimizer now performs update number 1. Every participating parameter moves by a tiny, carefully scaled amount.
Run the same context through the updated model. The token identifiers are unchanged, but the embedding rows and later weights may be slightly different. The residual stream follows a slightly different path. Attention scores shift, MLP activations shift, and the vocabulary logits shift. Suppose the probability of lake rises from 18% to 20%. The new loss is the negative logarithm of 0.2, about 1.609. For this example, the update moved in a useful direction. Real training does not normally rerun the same batch immediately just to display this comparison. The next step uses new data, and progress is judged over many batches and held-out evaluations. A parameter change that helps one example can hurt another. The goal is not to memorize each sentence independently, but to discover shared statistical structure that reduces average loss across the data distribution. The before and after comparison is valuable because it exposes learning as a concrete numerical change, not a mysterious accumulation of knowledge. Training operates on batches containing many token sequences. The embedding state now has shape batch by sequence by hidden width. Matrix operations process these examples in parallel, making efficient use of accelerator hardware. Each valid token position contributes a next token target, so one batch may generate thousands of losses before they are reduced to an average. Batching changes both engineering and optimization. Larger batches increase arithmetic efficiency and reduce noise in the gradient estimate, but they require more memory for activations. Smaller batches provide noisier updates that can sometimes aid generalization, but they may leave hardware underused. Gradient accumulation offers a compromise by processing several microbatches before applying one optimizer step. The effective batch then spans multiple forward and backward passes without keeping all activations in memory at once. Across these examples, gradients for shared parameters accumulate into one proposed direction. The optimizer applies another small update and the cycle continues.
The training loop has several separate resource costs. Parameter count determines how many learned values must be stored and contributes directly to the arithmetic required per token. A useful rough estimate for dense transformer training is about 6 times the number of parameters times the number of training tokens in floating point operations. The forward pass accounts for roughly 2 times parameters times tokens, and backward computation adds roughly twice that forward cost. Memory has a different ledger. Parameters occupy storage according to their numerical precision. Gradients require additional space. Atom commonly keeps 2 moment estimates, often at higher precision. Activations depend strongly on batch size, sequence length, hidden width, layer count, and which intermediates are saved. Activation checkpointing reduces memory by discarding selected intermediates and recomputing them during backward, trading extra compute for capacity. Distributed training adds communication. Workers must exchange gradients, parameters, or activation charts. A system can therefore be limited by arithmetic throughput, memory capacity, memory bandwidth, or network communication, even when the model equation is unchanged. Over many updates, training loss usually trends downward, but not in a perfectly smooth line. Batches differ in difficulty, gradient estimates contain noise, and the optimizer carries momentum from recent history. Monitoring, therefore, focuses on trends, stability, and comparison with held-out validation data. A falling training loss proves that the model is fitting the examples it sees. A falling validation loss suggests that the learned structure transfers to text it did not train on.
Generalization emerges because the model has limited parameters relative to the diversity of possible sequences.
and because the same weights must serve many contexts. Useful regularities can reduce loss across many examples at once. Memorization also occurs, especially for repeated or distinctive data, so data curation, deduplication, evaluation, and privacy controls remain important. Scaling model size, training data, and compute can improve predictive performance when balanced well, but the causal mechanism never changes. Produce distributions, measure their error, propagate gradients, and update shared parameters. After training, inference uses the learned parameters without computing gradients or optimizer updates. The user supplies a prompt, which is tokenized and embedded just like training text. Position information enters, transformer layers update the residual stream, and the output projection produces next token probabilities. The learned forward path is the same kind of computation, but the operational goal has changed. Training evaluates known targets in parallel. Generation must choose an unknown next token and then feed that choice back into the context. Because backward computation and optimizer state are absent, inference can use less memory than training. But serving introduces other constraints: response latency, concurrent users, long contexts, and repeated decoding. The prompt is processed in a prefill phase that handles many positions in parallel. Once the model reaches the end of the prompt, it begins decoding one new token at a time. This sequential dependency is fundamental because the next step cannot begin until the current token has been selected.
During autoregressive decoding, earlier attention keys and values do not need to be recomputed from scratch at every step. The system stores them in a key value cache. When a new token arrives, the model computes the query, key, and value for that new position. Its query attends to the cached keys, and the resulting weights mix the cached values. The new key and value are then appended for the next step. Caching reduces repeated arithmetic and makes generation practical, but it consumes memory that grows with sequence length, layer count, number of active requests, and the key value dimensions. Serving systems may group requests into dynamic batches, quantize cache values, or use attention variants designed to reduce this cost. The cache contains temporary state for a particular sequence, not newly learned knowledge. The model's parameters stay fixed. A fresh conversation begins with a fresh cache, while the same trained weights continue to define how every request is processed. The output distribution must be converted into a token choice. Greedy decoding always selects the highest probability token. Sampling treats the probabilities as chances, allowing lower-ranked candidates to appear. Temperature changes how concentrated the distribution is. A lower temperature sharpens differences and makes choices more predictable. A higher temperature flattens the distribution and increases variation. Top K and top P filtering can remove the long tail before sampling. These controls do not make the model more knowledgeable. They change how its learned distribution is traversed. For factual or deterministic tasks, conservative decoding may be useful. For creative tasks, some variation may be desirable. Regardless of the policy, the selected token is appended to the sequence. It becomes part of the context for the next forward step. The model does not draft an entire response in a hidden buffer and reveal it afterward. It repeatedly converts the current context into a distribution, chooses one token, extends the context, and continues.
Generation is an autoregressive loop. Begin with the prompt, predicted distribution for the next token. Select one token according to the decoding policy. Appended. Update the cache. Predict again. The loop ends when the model selects a stop token, reaches a length limit, or the serving system applies another stopping condition. Each generated token can alter what follows because it becomes input to every later prediction. A low probability choice can steer the continuation into a different region. This sensitivity explains both the flexibility and the instability of open-ended generation. The model remains a conditional predictor throughout. Its apparent long-form structure comes from learned patterns expressed across repeated local decisions. The complete path is now visible. Raw text defines next token examples. Tokenization supplies discrete units. Embeddings and position create state. Transformer layers mix and transform context. Logits become probabilities. Loss produces gradients. Optimization changes parameters. And frozen parameters later drive a cached token-by-token generation loop. A production language model is vastly larger than the tiny example. It may contain billions of parameters, dozens or hundreds of layers, large batches, long contexts, and distributed computation across many accelerators. Specialized kernels, mixed precision, checkpointing, parallelism, and serving infrastructure determine whether the system can run efficiently. Those engineering layers matter, but they do not replace the core learning mechanism. Text becomes tokens. Tokens become contextual vectors. Contextual vectors become vocabulary scores. Scores become probabilities. The observed next token turns probability into loss. Backpropagation turns loss into gradients. The optimizer turns gradients into parameter changes. Repetition turns small changes into a model that captures broad statistical structure. During generation, the model uses that structure one conditional token at a time.
Keeping this causal chain intact makes advanced details easier to place. Every new equation, architecture choice, or systems optimization changes some part of representation, prediction, error measurement, updating, or efficient generation. The learning mechanism can only respond to the examples it receives. If a phrase, language, programming pattern, or style appears frequently, it contributes gradients frequently. If it is absent, the next token objective cannot invent direct experience with it. Data composition therefore acts like a weighting system over possible behaviors. Duplication increases that weight, even when the repeated text adds no new information. Low-quality or contradictory material can spend compute teaching patterns that later require correction. Preparation pipelines filter documents, remove exact and approximate duplicates, classify content, balance sources, and construct train and validation splits. Tokenization then converts those choices into the actual sequence distribution seen by the model. Long documents may be divided into training windows, and boundaries can determine which relationships fit inside one context. Data quality is not separate from optimization. It changes the examples that create loss, the gradients that accumulate, and ultimately the regions of parameter space the optimizer visits. A model learns the statistical world represented by its training process, including that world's omissions and distortions. A training run exposes signals that reveal whether learning remains healthy. Loss should improve over a meaningful window, even though individual batches vary. Gradient norms indicate the overall pressure of an update and can reveal sudden explosions. Parameter and activation statistics can expose values drifting toward overflow, underflow, or numerical collapse. Throughput and hardware utilization show whether the system is spending its time on useful computation.
These signals must be interpreted together. A smooth training loss is not enough if validation performance worsens. High hardware utilization is not success if the data pipeline repeats corrupted examples. A gradient spike may come from an unusually difficult batch, an unstable learning rate, a precision problem, or a software defect. Checkpoints allow the run to recover from failures and support comparisons across training time. The causal model remains useful during diagnosis. Inspect the input distribution, the forward values, the loss, the backward gradients, the optimizer step, and the resource path. Each stage produces evidence about what went wrong. Validation loss measures how well the model predicts held-out text drawn from a defined distribution. It is broad and efficient, but it does not fully describe how the model behaves in use. Task evaluations examine capabilities such as reasoning, retrieval, coding, instruction following, calibration, or safety. Human review can assess qualities that are difficult to reduce to one automatic score. Robust evaluation therefore uses several views rather than treating one benchmark as the model's identity. The boundary between training and evaluation must be protected. If benchmark answers appear in the training data, the model may reproduce them without learning the intended general skill. Near-duplicate contamination can be subtle, especially when public material is copied across websites. Evaluations also become stale when systems are repeatedly optimized against the same test. A credible result records the prompt format, decoding policy, model version, and scoring method. Evaluation does not modify the weights during ordinary use. It observes the frozen model and asks whether the statistical structure learned through next token prediction transfers into reliable behavior.
When a language model produces an impressive answer or a serious failure, trace the result through the same chain. Ask what tokens entered and how the context was represented. Ask which transformations could combine the relevant evidence. Ask what training examples and objectives would have rewarded similar behavior.
Ask how decoding changed the final path through the probability distribution. Then ask which constraints, including context length, data coverage, computation, memory, and evaluation design, shaped the outcome. This method avoids two common mistakes. The first is treating the model as a database that simply retrieves complete stored responses. The second is treating it as an unexplained intelligence whose behavior cannot be connected to computation. A language model is a learned conditional system. Its parameters were formed by repeated gradient-based updates, and its outputs are formed by repeated probability-based token choices. The implementation is large, but the causal sequence is inspectable. Representation leads to prediction. Prediction leads to error. Error leads to updates. Updates create the fixed model that later generates one token at a time.